Hello everybody, and welcome to part 2 of our videos on the ellipse. So now we're going to take a look at ellipses that are not centered at 0, 0. Instead, they're centered at hk. And just as with any other function, the real difference here is going to be that we will have x minus h in place of x in our equation, and y minus k in place of y. Other than that, it doesn't change anything significant, and although I've placed this table here for your reference, nonetheless, I'm not really going to use this table. So if you'd like to copy it down and use this as your reference, you are welcome to. But we're going to move along and just take a look at the graphs again and see how that relates to the constituent parts. So here's a horizontal and a vertical graph. So these graphs, our center is HK here on the horizontal graph. And since this is horizontal, our distance A takes us out to our vertices along the X direction. So we're going to add A to H, and we get H plus A, K, for our new vertex. And then if we go backwards a distance of A, we get H minus A, K, for our second vertex. And if we go up by a distance of b, that gives us our minor axis endpoint, number 1, which would be h, and then k plus b. All right, we're adding b to the y value. And then for our other minor axis endpoint, which should be labeled m2 here, we're going to subtract b from our center and get hk minus b. Similarly, for our foci, since these foci are on the major axis, which is in the x-axis direction, we would be adding c to h here and get h plus c is k for one focus, and similarly we would get h minus c k for the other focus. Now for a vertical ellipse, we take a look at this ellipse on the right. And A is the distance from the center to the vertex. So since this is vertical, it's going to be h k plus A. And then for our other vertex, it'll be h k minus A. For our minor axis endpoints, we'll be adding B to the x value. That's h plus B, k. And then we'll be subtracting B. So that's h minus B, k. And similarly, our foci will be adding c along the y value. That's h k plus c and h k minus c. Okay, so let's move on. Find an equation of the ellipse satisfying the given conditions. Vertices at 0, 10 and 0, negative 2, and a focus at 0, 7. So let's go ahead and try to graph this. So we've got 0, 10. Oops, that's the wrong direction. Let me try that again. So 1, 2, 3, 4. Okay, so we should have one vertex up here. And we should have another at 0, negative 2. Okay, so that means the distance between these, which is 2a, is 10 minus negative 2, or 12. Right? And so a is 6, and likewise, our distance to our center is 6 from one of these vertices. So that would put our center at 0, 4. We have a focus at 0, 7. So let's kind of compile some of our information as we go here. So we know now that our value for A is 6. And we have a focus at 0, 7. That tells us that C, the distance from the center to the focus, is 3. All right, that's the distance from 7 to 4 here along the y-axis. So now I need to know what b is in order to find my equation. So we'll use our equation that b squared equals a squared minus c squared. So b squared equals 36 minus 9. So b squared equals 27. Now, of course, that means b is the square root of 27, but since I'm not graphing here, I only really need b squared to write my equation. Now, this is a vertical equation. We can tell, obviously, because our vertices are positioned vertically over our center. And that tells us we're going to have x minus h squared over b squared plus y minus k squared over a squared equals 1. Now, h is going to be 0 because our center is at 0, 4. So this is x squared over 27 plus, and k is 4 since our center is at 0, 4. This is y minus 4 squared over a squared, which is 36, and this is all equal to 1. All right, that's our equation. All right, now, given this graph, find an equation of the ellipse. Okay, so our graph is centered at negative 2, 2. And if we look at the distance vertically, that's a longer distance than the distance horizontally here. That tells us this is a vertical ellipse. And since it's shifted, it should have the form x minus h squared over b squared plus y minus k squared over a squared equals 1. All right, so if we look at our little distance here from our center out to this midpoint, or this minor axis endpoint, I should say, that's from x equals negative 2 to x equals negative 3. That's a distance of b equals 1. And similarly, if I look at the distance from my center up to my vertex up here, that's from y equals 2 to y equals 5, so I should have a equals 3 here. Putting all of this together, this gives me x minus negative 2 squared over 1 squared plus y minus 2 squared over 3 squared, which is 9. That gives me x plus 2 squared plus y minus 2 squared over 9 equals 1. All right, well, now that we've got that, let's take a look at something else. This is the general equation of the ellipse. So similar to the general equation of the hyperbola, this is basically where all of your terms have been multiplied out, and it's going to be much harder to figure out your information from your ellipse in this form. Now, this general form is ax squared plus cy squared plus dx plus ey plus f equals 0. Well, what are the conditions for it to be an ellipse? Well, the condition is that a times c has to be positive. That is, neither a nor c here are 0, and they both have the same sign. And that should make sense because that's the only way we'll get an equation that ends up with positives in front of both x and y squared. If they weren't the same sign, we would have one of these having a different sign than the other. One might be negative, one might be positive. Obviously, if they were both negative, you can always multiply an equation by negative 1 on both sides and not change the value of the equation, so that wouldn't be as much of a problem. Now, just like when we dealt with this with the parabola, we're going to need to complete the square here. But this particular completing the square is going to be a little bit harder of a process. So not too much, but just a little bit. All right, well, what I'm going to do first is group all of my x terms together, and then group all of my y terms together, and then put everything else somewhere else. So 9x squared plus 72x. Then I've got 4y squared minus 24y. And then I've got this 144 here, which I'll go ahead and move to the other side of the equation and make it negative 144. Now, my next step here is going to be to just factor out, because in order to complete the square, I really want this to just be x squared and y squared instead of having this leading coefficient. So I'm going to factor a 9 out of both of my x terms. It gives me 9 times x squared plus 8x plus 4 times y squared minus 6y. Now, in order to complete the square, I'm going to have to add and subtract b over 2 to each of these polynomials, just like I did before. But first, let me just write a little gap here for each one. Okay, so b for my polynomial involving x squared, b is 8. So we want to add and subtract b over 2 squared. So that's 8 over 2 squared and minus 8 over 2 squared. Right, because what we're really doing here, remember, is we're just adding 0. Similarly, for our polynomial involving y, we're going to add 6 over 2 squared and subtract 6 over 2 squared. So this gives me 9x squared plus 8x plus 16 minus 16 plus 4y squared minus 6y plus 3 squared, which is 9, minus 9. And be careful not to try combining these, because the whole purpose was to get this trinomial here that can be factored perfectly. Right? We get the perfect square factors for that. So this becomes 9 times x plus 4 squared minus 16 plus 4 times y minus 3 squared minus 9. Okay, now you should notice that you've got this minus 16 trapped in here, and we need to simplify how this equation is written. So we're just going to distribute this 9 to both terms and this 4 to both terms. This gives me 9x plus 4 squared minus, and 16 times 9 is going to be 144, plus 4y minus 3 squared minus 36, all equals negative 144. So those negative 144s on each side of the equation cancel each other out, and then I'm going to move my 36 over. So I get 9x plus 4 squared plus 4 times y minus 3 squared equals 36. And lastly, I just need to divide each side by 36. And now I have x plus 4 squared over, that's going to be 4, plus y minus 3 squared over 9 equals 1. Okay, so that's our equation. Well, that was a lot of hard work. But now we need some more information. We need the center, the foci, and the vertices. Well, the center's pretty straightforward. That's at -4, 3. All right, we've got x plus 4 and y minus 3, so our center is at -4, 3. Okay, now we need to know what A and B are. So this is vertical, since the larger number is paired up with the y, so A is equal to 3, and B is equal to 2. And we'll go ahead and start drawing our graph and then figure out our foci and our vertices from there. So if the center is at -4, 3, that's going to put the center right here. And since it's vertical, our vertices are going to go in the y direction by a distance of 3. So we're going to go just up 3 for our first vertex and down 3 for our second vertex. So our first vertex then would be at -4, 6, and our second would be at -4, 0. Now our minor axis endpoints will be out a distance of b. So I'm going to go over b, and which is over 2 to the right, and then 2 to the left. So one of our endpoints will be a -6, 3, and the other will be a -2, 3. And lastly, I need to find my foci, which means I need the distance c. So b squared equals a squared minus c squared. So 4 equals 9 minus c squared. So c squared equals 5. And c is the square root of 5. So that means our distance is going to go out from the center, up by a square root of 5 and down by a square root of 5. Square root of 5 is a little bit bigger than 2, so that's going to be kind of right here. So we'll put one focus here. It's going to be at, let's see, that's -4 and then 6 plus the square root of 5. Or sorry, 3 plus the square root of 5. I apologize. 3 plus the square root of 5. And then our other one will be down here. And that'll be -4 and 3 minus the square root of 5. Let me just zoom in a little on that. And our graph will just be connecting our vertices and our minor axis endpoints like that. All right. Well, that's a pretty challenging one. Let's go ahead and take a look at one more example here. We're going to talk about what's called the reflecting property for ellipses. So this is sort of similar to the reflecting property for parabolas, except this says that if you have an elliptical shape and you take a wave, like a sound wave, from one of the focal points on the ellipse, then that wave will bounce off the ellipse and bounce back to the other focal point. All right, so let's put that into place. Let's use that. The vertical cross section of the dome of a building is semi-elliptical in shape. The cross section is 250 foot long with a maximum height of 80 feet. Where should two people stand to maximize the whispering effect? So that's what we call this reflecting property for ellipses, the whispering effect. So this just means find the foci. Well, I'm just going to draw the vertical cross section. Now, I'm going to center this at 0, 0, because that, of course, makes things easier. And the height is 80 feet here. Now, this entire distance horizontally is 250 feet. But that means that the distance from the center is 125. So 125 is my A, and 80 is my B. So if I want C so that I can find my foci, I'll solve B squared equals A squared minus C squared. So 80 squared equals 125 squared minus C squared. I'll move the C squared over and subtract 125 squared minus 80 squared. And that's definitely calculator work. So let's go ahead and tackle that. One moment. So for C squared, I get 9,225. So, well, C is exactly the square root of 9,225, which is approximately 96.05 feet. So we might word this in one of two ways. Either the people should stand at plus or minus 96.050 at the two foci, or we might say they should stand 96.05 feet from the center in either direction. Well, that's it for this video on ellipses. Thank you for watching.